Lake Oroville is climbing toward a level that only a handful of Californians have witnessed in modern times. The immense reservoir behind America's tallest dam is now sitting at nearly complete capacity, and the water is still rising. Across Northern California, boat ramps stretch farther into deep blue water than they have in years. Shorelines that once exposed dry earth and pale rock during drought emergencies are submerged again. Marina docks float high. Tributaries feeding the reservoir continue carrying spring runoff out of the Sierra Nevada. Snowmelt, storm runoff, and carefully managed releases have combined to push the state's second-largest reservoir to a threshold that carries enormous significance for California's economy, agriculture, flood protection system, and long-running battle with drought. How often does a reservoir this large approach total capacity 4 years in a row? How much water is actually sitting behind the towering Oroville Dam when the lake reaches nearly 100% full? And after years of severe drought, dangerous wildfire seasons, shrinking snowpack, and historic water restrictions, what does this dramatic turnaround reveal about the changing balance between California's wet years and dry years? The answers extend far beyond a single lake in Butte County. Lake Oroville is not simply a regional reservoir serving nearby communities. It is one of the most important water storage facilities in the United States. The reservoir is a cornerstone of the California State Water Project, a vast network of canals, pumping stations, dams, and aqueducts that delivers water to millions of residents and enormous agricultural regions stretching hundreds of miles to the south. When Oroville rises, California's water outlook changes with it. When it falls, concern spreads quickly across farms, cities, and state agencies. During the middle weeks of May in the year 2026, Lake Oroville reached approximately 99% of its total storage capacity. State water officials reported that the reservoir held roughly 3.38 million acre-feet of water, placing the lake at more than 120% of its historical average for this point in the year. The lake elevation approached 897 feet, leaving only a narrow margin before reaching the operational maximum associated with a completely full reservoir. The sheer volume involved is difficult to visualize. 1 acre-foot equals enough water to cover 1 acre of land to a depth of 1 foot. In metric terms, a single acre-foot equals about 1,233 cubic meters of water. Multiply that by more than 3 million, and the reservoir contains a quantity so massive that it becomes comparable to an inland sea. Lake Oroville can store roughly 3.5 million acre-feet at full capacity, equivalent to more than 4.3 billion cubic meters of water. The lake stretches across approximately 167 miles or 269 kilometers of shoreline when full, winding through steep foothills and flooded river valleys north of Sacramento. The enormous body of water exists because of Oroville Dam, the giant earthfill structure completed during the late 1960s as part of California's ambitious State Water Project. Rising approximately 770 feet or 235 meters above the Feather River, the dam remains the tallest in the United States. It transformed the Feather River Basin into one of the central engines of California's modern water system. Water captured there supports agriculture in the Central Valley, helps maintain freshwater flows through the Sacramento-San Joaquin Delta, contributes to hydroelectric generation, and eventually supplies homes and businesses hundreds of miles away. Lake Oroville's rapid recovery during recent years represents one of the most striking reversals in California's ongoing cycle of water extremes. Only a few years ago, the reservoir looked dramatically different. During severe drought periods earlier in the decade, water levels plunged so low that marinas sat stranded on exposed mud and rock. Boat launches closed. Large portions of shoreline that had remained underwater for decades reappeared. Satellite images showed enormous pale rings around the reservoir basin where water had retreated. Concerns intensified about water allocations, hydroelectric generation, fisheries, wildfire conditions, and the long-term resilience of the state's water infrastructure. In some periods during the drought emergency, Lake Oroville fell to levels that shocked even long-time observers. Reservoir storage dropped to a fraction of capacity as California endured years of limited precipitation, shrinking snowpack, and extreme heat. The Sierra Nevada snowpack acts as one of California's most important natural water storage systems, gradually releasing meltwater into rivers and reservoirs through spring and summer. When snowpack declines dramatically, reservoirs like Oroville struggle to refill. The transformation from those critically low conditions to near-complete capacity did not happen overnight. California entered a series of wetter years that steadily rebuilt water storage across much of the state. Atmospheric river storms repeatedly swept into Northern California during winter seasons, delivering immense volumes of rainfall and mountain snow. Reservoir inflows increased dramatically. Snowpack measurements improved. River systems that once carried unusually weak flows began surging again. Each successful winter added another layer of recovery. By the time the current year arrived, Lake Oroville had already experienced multiple seasons of healthy replenishment. The reservoir approaching full capacity for the fourth consecutive year marked an especially significant milestone because such consistency is rare in California's climate history. California has always operated within a climate of sharp extremes. Long dry periods are frequently interrupted by intense wet years capable of transforming the state's hydrological outlook in only a matter of months. Reservoir managers must constantly balance competing priorities. They need enough storage to prepare for drought, enough empty space to absorb floodwater during major storms, and carefully controlled releases to support ecosystems, downstream communities, agriculture, and urban demand. Lake Oroville sits at the center of that balancing act. Every adjustment in reservoir operations carries consequences downstream. Water released through Oroville Dam enters the Feather River system, before eventually contributing to broader statewide water management operations. The reservoir also supports hydroelectric generation through the Edward Hyatt Power Plant, one of the largest underground hydroelectric facilities in the nation. As water levels rise, operators monitor inflow and outflow with increasing precision. Reservoir management becomes especially delicate when the lake nears full capacity during spring snowmelt season. Snow remaining in the Sierra Nevada continues melting as temperatures climb. Additional runoff enters tributaries feeding the reservoir. If late-season storms arrive on top of melting snowpack, inflows can rise rapidly. That reality explains why officials continue carefully regulating releases even while celebrating the strong water supply outlook. Maintaining flood control space remains essential. Reservoirs are not simply filled to the top and ignored. Operators constantly evaluate weather forecasts, snowpack conditions, downstream river capacity, environmental requirements, and dam safety considerations. Those safety considerations remain deeply connected to one of the most serious infrastructure crises in recent California history. In the year 2017, Oroville Dam became the focus of national attention after heavy winter inflows severely damaged the main spillway. Large sections of concrete failed as water rushed down the spillway channel. Soon afterward, water began flowing over the emergency spillway for the first time since the dam's construction. The emergency spillway situation triggered enormous concern because erosion rapidly developed below the concrete overflow structure. Authorities feared that continued erosion might threaten the spillway itself, potentially unleashing uncontrolled flooding downstream. Emergency evacuation orders spread across communities below the dam. Nearly 200,000 residents were told to leave the area as crews worked urgently to stabilize conditions. Images from that crisis became some of the most dramatic infrastructure photographs seen in California in decades. Massive scars opened along the damaged spillway channel. Heavy equipment crowded the hillside around the reservoir. Water releases intensified as operators attempted to lower the lake while protecting the compromised structures. The crisis ultimately led to one of the largest dam repair operations in modern American history. California launched an enormous reconstruction project involving excavation, concrete replacement, structural reinforcement, erosion protection, and extensive redesign work around the spillway systems. The repairs cost well over $1 billion and required years of construction. That history still shapes public attention whenever Lake Oroville approaches full capacity. Rising water levels now trigger a very different reaction than they did during drought emergencies. Instead of concern about empty reservoirs, many residents watch closely to ensure that infrastructure upgrades and operational strategies can safely manage another sequence of heavy inflows. State officials insist the rebuilt spillway system is designed to handle major flows safely. Since reconstruction efforts were completed, the reservoir has repeatedly approached or reached very high levels without repeating the failures seen during the crisis period. Still, memories of the evacuation remain deeply embedded in public consciousness throughout Northern California. The current near-full conditions also highlight how dramatically California's broader water outlook has changed compared with the worst drought years. When reservoirs shrink, the consequences ripple across almost every sector of the state's economy. Agriculture faces reduced allocations, groundwater pumping intensifies, hydroelectric generation declines. Fish habitats suffer under warmer and shallower river conditions. Wildfire risks often rise as vegetation dries earlier in the season. By contrast, reservoirs near capacity provide a much stronger operational cushion entering summer. Water agencies gain greater flexibility in managing deliveries. Hydroelectric facilities can generate more electricity. Recreational activity expands around lakes and rivers. Fisheries often benefit from improved cold water storage and healthier flows. The recreational impact around Lake Oroville alone is substantial. As water levels recover, boating access improves dramatically. Campgrounds, marinas, fishing areas, and shoreline recreation zones become more active. The reservoir supports a significant outdoor tourism economy in Butte County and surrounding regions. Businesses connected to boating, camping, fuel sales, food services, and outdoor recreation tend to benefit when the lake remains high through summer. Fishing activity often increases as well. Lake Oroville is widely known for bass fishing and supports populations of multiple fish species, including salmon, trout, catfish, and crappie. Nearby fish hatchery operations also play an important role in supporting regional fisheries connected to the Feather River system. Yet the reservoir's importance extends far beyond recreation. Water stored behind Oroville Dam helps serve approximately 27 million Californians. The State Water Project distributes water to urban districts and agricultural users across enormous portions of the state, including parts of the San Francisco Bay Area, the San Joaquin Valley, and Southern California. That distribution network represents one of the most ambitious water engineering systems ever constructed. California's population centers and agricultural regions are often located far from the state's largest natural water sources. Northern California receives much of the state's precipitation, while drier southern and central regions consume enormous quantities of water. Reservoirs like Oroville function as giant collection and regulation systems, allowing water to be captured during wet periods and redistributed during drier months. The significance of near-full storage becomes especially clear when examining California's historical volatility. The state has experienced repeated swings between flood emergencies and severe drought. In some years, atmospheric river storms deliver extraordinary rainfall totals capable of overwhelming rivers and infrastructure. In others, snowpack collapses and reservoirs decline rapidly. Climate patterns are increasingly amplifying those swings. Warmer temperatures can intensify evaporation, reduce snowpack retention, and shift precipitation from snow toward rain. At the same time, stronger atmospheric river events may deliver larger bursts of rainfall over shorter periods. That means California's reservoirs face a growing challenge, capturing enough water during increasingly intense wet years while still maintaining sufficient flood protection. Lake Oroville's current status therefore represents both a success and a warning. The reservoir's near-complete recovery demonstrates how quickly water conditions can improve after major storm sequences. But it also illustrates the immense pressure placed on infrastructure systems that must manage increasingly volatile hydrological extremes. Throughout spring, operators continued adjusting releases from the reservoir while tracking runoff entering the Feather River Basin. Water flowing downstream supports multiple purposes including environmental management, agricultural supply, and flood control coordination. Every release decision involves careful calculation because storing too much water can reduce flood protection flexibility, while releasing too much may waste valuable storage before dry months arrive. The scale of Oroville's watershed contributes heavily to these operational challenges. Tributaries feeding the reservoir drain large portions of the northern Sierra Nevada. Snow accumulation across higher elevations gradually melts as temperatures rise through spring and early summer. Even after winter storms end, inflows can remain elevated for weeks because of delayed snowmelt runoff. This year's conditions have been especially favorable for maintaining strong storage. Successive wet winters provided a solid foundation before additional spring inflows continued pushing the reservoir upward. Measurements showed the lake remaining well above historical averages for the season. The achievement becomes even more remarkable when compared with previous eras of sustained high storage. Records indicate that 4 consecutive years of near full or full conditions had not occurred since the late 1990s. Before that, similarly strong sequences were observed during earlier decades following particularly wet periods. California's hydrological memory often operates in cycles. Wet decades can create a temporary sense of security, while drought years rapidly expose vulnerabilities. The state's infrastructure was built partly to smooth out those fluctuations, but population growth and climate variability continue testing the limits of the system. Oroville Dam itself emerged from an era defined by large-scale infrastructure ambition. Construction began during the 1960s as California pursued enormous water development projects designed to support agriculture, urban expansion, flood control, and economic growth. Engineers transformed the Feather River Valley using millions of cubic yards of earth and rock to create the giant embankment structure. The resulting reservoir became the largest storage facility within the state water project system. Water captured there supports aqueducts and pumping systems extending across hundreds of miles. Hydroelectric generation from the Oroville Thermalito complex also contributes substantial electricity production. Maintaining such infrastructure requires constant monitoring and investment. The spillway crisis revealed how aging systems can encounter unexpected vulnerabilities under extreme conditions. Since then, state agencies have intensified inspections, maintenance programs, and operational reviews tied to dam safety. Public scrutiny has also increased. Residents downstream of the dam pay close attention whenever major storms strike Northern California. During heavy rainfall events, updates regarding reservoir levels, spillway operations, and downstream releases attract statewide attention. Current reservoir conditions are far less alarming than those seen during the emergency years. But they still generate intense interest because Lake Oroville occupies such an important place within California's broader water picture. High storage levels entering summer reduce immediate drought anxiety and provide reassurance that water supplies remain strong heading into hotter months. For agriculture, that reassurance matters enormously. California's Central Valley produces a vast share of the nation's fruits, vegetables, nuts, and other crops. Irrigation demand remains immense, especially during dry summer periods. Reservoir storage across the state water project system influences allocation decisions that directly affect farming operations. Urban users also depend heavily on stable water deliveries. Millions of households rely indirectly on reservoirs like Oroville, even if they live far from Northern California. During drought emergencies, water restrictions often become a visible reminder of how interconnected the state's water system truly is. Hydroelectric generation adds another layer of importance. Water released through the Oroville Thermalito system powers turbines capable of producing significant electricity. During periods of high reservoir storage, hydroelectric output generally becomes more reliable. That matters in California's broader energy landscape, especially during summer demand peaks driven by air conditioning usage and extreme heat. Environmental considerations remain equally significant. Reservoir operations affect river temperatures, fish migration patterns, wetland conditions, and delta ecosystem management. Balancing human demand with environmental protection has become one of California's most difficult long-term policy challenges. Cold water storage within reservoirs can prove especially important for fisheries downstream. During drought periods, warmer river temperatures often stress salmon populations and other aquatic species. Higher reservoir levels can improve management flexibility for maintaining healthier downstream conditions. Despite the encouraging outlook, officials understand that California's water fortunes can reverse quickly. A few wet years do not erase the state's long-term exposure to drought. Reservoirs filled today can decline rapidly during prolonged dry periods, particularly under hotter climate conditions. Historical records show repeated examples of dramatic swings. Reservoirs once considered comfortably full have later fallen to alarming lows within only a few seasons. That volatility explains why water managers continue emphasizing conservation, infrastructure modernization, groundwater recharge efforts, and long-term planning even during strong water years. Still, there is no denying the visual and operational significance of Lake Oroville approaching complete capacity once again. A reservoir that seemed dangerously depleted during recent drought emergencies now sits near the top of its storage range. Water laps against shorelines that had once retreated hundreds of feet or dozens of meters away. Boat docks float high where dry mud had previously cracked under intense summer heat. The contrast reveals how quickly California's water landscape can change. Atmospheric rivers and strong snowpack years transformed the outlook within a relatively short period. The same reservoir that symbolized drought vulnerability has temporarily become a symbol of abundance. Yet abundance in California often carries its own complexities. Large reservoirs must be managed carefully during wet periods because the line between valuable storage and dangerous flooding can narrow quickly during major storm events. Reservoir operators continually balance the need to conserve water against the need to protect downstream communities. Today, with the lake nearing total capacity once again, attention has returned not to collapse fears, but to operational success. Reservoir managers are navigating another high water year while monitoring snowmelt inflows, downstream conditions, and spillway performance. As summer approaches, California enters the warm season with one of its most important reservoirs essentially full. The significance reaches far beyond Butte County. Farmers hundreds of miles away, urban water districts, hydroelectric planners, recreation businesses, and environmental managers all watch Lake Oroville because its water level influences decisions across enormous portions of the state. For now, the outlook remains strong. The reservoir stands near the top of its operational range after consecutive wet years restored storage levels that once seemed dangerously depleted. Spring runoff continues feeding the lake. Infrastructure rebuilt after the spillway crisis is being tested under real-world high water conditions. And California, at least temporarily, holds a far stronger water reserve than many feared possible during the harsh drought years earlier in the decade. The lake is still rising,